In this video, we'll look at the continuity of a function and what that means. This will be an important section with a definition that we will use again and again throughout the course. So let's start with the definition. A function is considered continuous at a number a if the limit of the function as x approaches a is equal to f of a. So here's an example that if we wanted to make a statement that shows that a function is continuous at a, we could say that the limit of f of x as x approaches, let's pick some number 5. The limit of f of x as x approaches 5. If the limit of f of x as x approaches 5 is equal to f of 5, then we can say that f, the function f, is continuous at 5. So if you wanted to state, if you wanted to make a statement that shows that f is continuous at, let's say, some number 7. What statement can you make to show that f is continuous at 7, to demonstrate that f is continuous at 7? Say that the limit of f of x as x approaches 7, it's not that it equals 7, it equals f of 7. So let's let f equal x plus 3. That's how we'll define our function. What statement could you make to show that f continuous at 10? If f is continuous at 10, let me move the page up just a bit. If f is continuous at 10, then the limit of f of x as x approaches 10 would have to be equal to f of 10. Now let's look at each of these two pieces and see if they are in fact equivalent. What is the limit of f of x as x approaches 10? We can use direct substitution and say that if f of x is x plus 3, we can replace the x with 10 and get 13. So the limit of f of x as x approaches 10 is equal to 13. Let's now look at what the value of f of 10 is. F of 10 will replace the x with 10, the same. 13 equals 13. So we can say that f of x is continuous at 10. Oh, I'm sorry, we ran off the page here. Because f of 10 is equal to 13, and the limit of f of x as x approaches 10 is also 13, because 13 and 13 are equivalent, we can say that f of x is continuous at 10. It may seem easier to comprehend, to understand this definition when we move on and we look at some functions that are not continuous. But for right now, let's pull out what 3 things that definition is implying. Let me put the definition back up. But this for a continuous function, a function being continuous at number a, would have to follow, really implies these 3 different pieces. First, f of a has to be defined. And then next, the limit of f of x as x approaches a has to exist. So both sides have to be defined, or both have to exist. And then the third piece is the limit of f of x as x approaches a has to be the same as the limit of f of a. So this definition really implies three qualifications to be continuous at a number a. F of a is defined, the limit exists as x approaches a, and the limit equals f of a. Let's look at some examples of, or let's look at a function that's not continuous at a. This function is not continuous in three different places. Can you see the three places where this function is not continuous? It's not continuous at 1 because f of 1 isn't defined. Let me pull up those three definitions again, and we'll keep this here on the same screen. So at a equal to 1, f of 1 isn't defined, so this function is not continuous at 1. We're not continuous at 3. When a equals 3, it's not continuous because f of 3 exists, but the limit doesn't exist. Notice that the limit from the right and the limit from the left have two different values. So in this case, for a equal 3, the limit doesn't exist. And then we have a third example of a discontinuity. The function is not continuous at x equals 5 because although the limit exists, notice that the limit as x approaches 5 from the left or from the right is equivalent. So we have that the limit exists, and we have that f of 5 exists, but the problem is that the two, they're not equivalent. So f is discontinuous at 5. Let me show you a few more examples of discontinuous functions. In this first example, example A, this type of discontinuity is called a removability. The reason this is removable is because we could remove the discontinuity by redefining f at just that single value 2. If we wrote this as a piecewise defined function, instead of just f of x equals x squared minus x minus 2 over x minus 2, we'd have to equal that rational expression when x isn't equal to 2. And then if we found what 2 squared minus 2 minus 2 all over 2 minus 2, if we put that value in and found without that discontinuity, what does the value appear equal? And we filled it in with that number. Then when x equaled 2, we define this function a number value. If we plug in a number value there, then we we remove that discontinuity. So we're just going to plug the function in at that open space. Now we could say that function is continuous. So that would be a removable discontinuity. Here's another example of a removable discontinuity. If we redefined the function to equal 1, rather than equaling 1 here, if we moved that value up to the fill in the hole here, that's called a removable discontinuity. Example B is what we would call an infinite. This is the function isn't continuous in this range because the function is approaching infinity. So we could call this an infinite discontinuity. And then one other type of discontinuity, example D. This is what we'd call an discontinuity, because we're jumping when x equals 0, we're jumping from down here up to here. When x equals 1, we jump up to y equal to 1. So we have a jump, or a jump discontinuity. Let's look at a couple theorems quickly. Using direct, we could find a proof for this theorem that any polynomial is continuous everywhere. That is, it's continuous on all real numbers from negative infinity to infinity. So if a function is a polynomial, it's given that it's continuous. We don't have to do anything to prove that. We can just simply state this theorem. A rational function, we don't have to do anything to prove that it's continuous. All we have to do is show that it's defined at whatever value we're showing that it's continuous. And that theorem number 5 would give us that the function is continuous. Theorem 7 gives us 4 types of functions that are continuous everywhere in their domain. So this will come in handy when you're doing the homework and you're asked to show that functions are continuous and why. If you're given an example that's a polynomial, the why is it continuous? So you could simply state by theorem 7. And then the last thing this video will touch on is the intermediate value theorem. We'll talk a lot more about the intermediate value theorem in class, but for now, let's just keep make sure that you've written that and that you've read through it a few times. And when we get to class, we'll discuss the intermediate value theorem more thoroughly. Thanks for watching this video. If you have any questions about the examples that were shown, please ask those questions in class, or you could also send an email before class. Thank you.